your position on this. Thank you.
Well, thank you for your insights, David, and thank you for your questions, Wolfgang. We need to go on. Our next speaker is Mark Simpson. Mark has had a keen interest in astronomy since he was about 8 years old when he saw his first meteor shower. And he, since then, has developed it by doing a lot of astrophotography. And he mentions that he has made astronomical images when the ambient temperature in the Canadian prairie was negative 35 degrees Celsius. So he is a dedicated astrophotographer. He began to observe asteroidal occultations this year, and he has been working on a device using a Raspberry Pi device for the timing of asteroidal occultations. And so, Mark, if you're ready, we want to hear what you have to say.
Hear me?
Hear you just fine.
That's a good start, okay. Well, thanks so much for the introduction, Roger. Okay, then, so I'm just going to share my screen here. Can you see it?
That looks very frightening.
Oh, sorry, that's my life. There you go, there you go. Is that better? As long as you can see things. Okay, so
I'm not seeing your screen.
you're not seeing the screen. Okay.
I was, Roger, now I only see you.
Okay. It says it's sharing at the moment.
I see it.
Okay. Do you see the keynote when I switch to the key?
I see a picture of a tornado, what looks like a tornado.
Okay, it should be something else on there then.
Yeah, I think most of us are just seeing your avatar.
Okay. I'm going to try disconnect and reconnect again. Okay. Okay. Did you have any problem screen sharing here? Okay. What about now?
Now I see your screen.
Okay,
Yep.
okay, awesome. All right then. Great. Okay, so as Roger said, sorry. So my name's Mark Simpson. I'm going to talk to you today about a device I've been working on called ASTRID, short for Astro Imaging Device.
Mark, let me just interrupt for just a moment. There is someone who is not muted, and I want to make sure that everyone has their microphones muted except for Mark at this time. Thank you for that.
Okay, so I've been working on a device called ASTRID, which is short for Astro Imaging Device. And hopefully this can become the next generation of TE. So there's a lot of information to get through in a few videos. So please any questions to the end. And this follows on quite well from Dave Harold's talks both yesterday and today. And hopefully it's going to address some of the data inconsistency he's with timing and position and things like that, and just quality that's being said to him. Okay, I'll tell you a story. So on the 19th of February here, I got contacted by some three other people in the RASC about an occultation. And it was like 11 o'clock in the morning, and the occultation was that evening. I hadn't got a clue about anything about occultations at all, right? So it was PKA occulting 40 Leonis, and it was just quite a bright star. The first, but I had no camera because I was sent back to the ZW over repair. All I had was a planetary camera. I had no experience, no clue at all. I had to find the equipment, but I didn't have ideal equipment, and I had to figure out the method to do an occultation. And first thing I found out was best practice was an older analog camera with a GPS timestamp, which I didn't have. So we learned was that scientists need data, that amateurs are resourced for getting this data, and also these are very rare events, and it's kind of a one-shot deal. You either get it or you don't. If you have any problems and you're sending stuff up, basically you miss it. Yeah, so we have 4 Calgary RST members, one of which so iPhone, they were using screen times because they were using an EV scope. The other one had an iPhone and Arduino GPS flasher. The other guy had QHY GPS cam, and I had all it was a ZWO plan cam and an iPhone flasher. So the following week, after I got the data, so it was actually a success. I did get some data. So following week, I had to learn the software to analyze the light curve. It pretty much took me most of a week. Figure out accurate stamping on all the videos because there were some issues with all the videos. Figure out how to submit reports. And the problem I encountered was cell phones have variable frame rates. So although mine wasn't a cell phone, 2 of the others and variable frame rates means it's very difficult to actually get accurate timing. The QHY that one people had required a frame date, so a firmware update. So that was problematic because they couldn't really trust too much of the data we're getting from that either without firmware update. Problems getting that firmware from QHY. One of the other ways was using EV scope raw video. However, all they had was the screenshot of the app recording on their phone, which again, screen recording is variable rate and quite, it does vary quite a bit. They went to get the EV scope raw video, and they never got it. So they never were supplied with the raw video of the data they acquired, which is unfortunate because it would have been useful. Then we could have determined timing, but because one of the occultations that EV scope concentrate on, we couldn't get that. What we figured out on the iPhone video was that the timestamps were really only accurate to about 1 second. And even if you had NTTP timing on the iPhone, best case was about 50 to 200 seconds accurate on the time. The other thing was poor video quality because you have compression going on as well. So obviously there's some of the data as well. Also, there's no easy way to tell for star saturation. So obviously, if the data is clipping, that's very difficult to get any brightness measurement or brightness measurements. And the other thing that was the other thing that happened obviously is timing issue. And also the software is pretty complex to learn as well. It raised questions about what was the best hardware setup to this. One using a DOB. I was using a Cat 71. So there's quite a variety of hardware out there. I needed extensive help from the others to figure out how to use the software to report the light curve. Now, given that this only happens infrequently, maybe a few a year, chance of me forgetting how to do that next time was pretty high. So I had to take extensive notes on it. And it's really difficult to get this stuff right? High anxiety as well. You get it wrong, you kind of waste your time for a second or two. Also, it's hardware for single use. To start getting dedicated video cameras and GPS flashes and things like that for a single use is costly as well. So what are the results? So what we figured out was that all this impacts the quality of the scientific. So as Dave Harold has said, that's his main concern coming in, and my concern as well that we're providing data, it should at least be accurate. It's essentially unusable. No point in bothering if we're not getting data that's good. The other thing as well is, and this isn't anybody's fault, but obviously data collected, but you don't necessarily get direct feed or or a consensus on maybe the correct way to do things. So essentially unaware of what's right and what's wrong. The people collecting the data are unaware of that, certainly when they're new to it. Also, those errors, say a mistake's being made in the acquisition, that error is likely to persist going forward unless that person actually told, hey, you're doing it wrong. But there's also a variety of ways of doing it as well. So that results in a lot of missed opportunities, being collected, and some percentage of that data is being thrown out for those reasons, and obviously that's a missed opportunity. The other thing as well is I concluded it was a bit of a barrier to adoption as well. It was easy for me, and and all this software is evolved over time as well, which is another thing in the processes over the time. But obviously, somebody into it isn't necessarily aware either. And the other thing I found out while the analog is going away, the cameras now difficult to get hold of, because generally people, camera manufacturers switching over to digital sensors. And the other one is time-based accuracy. That time-based needs to be accurate. So the wish list. So it needs to be something that's cheap and easy to repair for start. I don't want to spend like $1,000 to $2,000 on a camera that, if it breaks, I've got to send it back and get repaired. Rather be able to do it myself and fix it. I want it to do double duty. So it'd be nice if when I'm not using it for occultations, I could also be using it for stuff too, right? Ability to make them and share with people. Often it's good to have a little like we have a store for people that go out and do occultations, and kind of nice because you're getting enough records on an event as well, right? So having the ability to make these up fairly cheaply, share with people, and an advantage. Really something that does the heavy lifting. It's something that does go to polar alignment. Controls the mount, things like that, right? And it has the astrometry solution built in as well, right? The other thing that'd be nice is be able to switch out camera sensors. It's nice to have one thing, but say switch out to a different sensor for different purposes with the same device. And it'd be nice to have the sensors cheap as well. Who wants to pay $500 to $1,000 for a sensor? It'd be nice if we could just get something that's a cheap sensor. There are solutions out there that do similar things, but they're not occultation centric. So it's like the SIA, Nina, the main Strawberries out there, but they don't quite do everything that we need to do in one package. The other thing that'd be nice to have is roll shutter and global shutter. Rolling shutter can have time issues, which can be addressed, but essentially just nicer to use a global shutter and have the image all taken at the same time. The other thing we want is accurate timing. It'd be nice to have a single unit and no wires. I don't want to be hooking up laptops and like that. I want to have the ability to connect via laptop wireless, or say via an iPad wirelessly or an iPhone wirelessly. Basically, any that's mobile would be good, and then we'd have a permanent connection to anything. The other thing would be nice would be public outreach. So the ability to just hook up an external display when you're out there, if there's other out there as well, so they can see the started on that display would be nice. And it's kind of nice, the concept of having your own camera somebody could build. Is kind of ideal for a beginner because they're kind of then invested in the technology as well, right? And the other thing as well, it to be easy, consistent, and have a quality assurance process, so that when we're getting data and files, that data can be validated independently necessary. So introducing ASTRID. So what it's based on is a Raspberry Pi 4 plus a camera plus timestamping, all in one unit.
Mark, can I interrupt for just 1 second and ask if it's possible that you might have two sessions open, we are hearing sort of many of your words twice, and it may be that maybe there's a phone with another session into this same Zoom call.
Mm-mm.
If
Or
not, then
it could be that his speaker on his computer is turned up loudly. And
I'm
it's
actually
recording onto his microphone a second time.
I'm actually on headphones, so the speaker should be off. I'm just going to check. The speaker off. The phone is off. The earbuds are off. So I've only got one connection in. It's just a single phone, and I've got headphones on the output. So is it still on double?
yes, but apparently there's nothing we can do about it. We do understand you, so
Okay.
go ahead.
I could try muting myself and see if that happens again, or should I? Could try stopping the screen and restarting that. Maybe I'll just try. Is that any better? Is that any better?
Well, I don't hear the duplicated speech at this time, but it may be that we need a further test.
Okay, fair enough. Well, I just muted and unmuted again. Let's see if that works.
I think it does sound a little better.
That's strange. So there's no technological reason this end anyway. So where was I? Let's just go back to. So the unit plugs straight into the eyepiece, or it can be attached to a DSLR lens as well. So essentially, you've got one single unit that contains everything. Just plug into the telescope. It's got a wireless connection. Currently, that's via VNC. Similar kind of idea to a desktop. I'll do an iPhone app later. It's designed for occultation or astrophotography, so you can do double duty. There's a recorder app, an OTE recorder app designed for occultations, and a OTE still board, which is needed for timing occultations. It's a double shutter. It has highly accurate time, including frame pulse. So one of the problems with with the exception of a PS camera like the QHY1, most of the USB cameras out there, you can't get accurate frame timing on because there's a delay when it's sending a frame and it's communicated to USB and the OS recognizes it. So this actually has via the time board and the sensor using actually has a vertical signal that comes out of camera, and that's timed extremely precisely. So we do actually know what time that frame was taken, even if it's processed a few milliseconds later. Also, it has a LED built in as well, which is I'm using for testing and verification purposes. Probably won't need there in the final product, but can be used. So that would be a similar kind of idea to the flash LED that you see on the GPS flashes that's been making. It's written in Python. As much as I hate Python, I'm really a C program, but Python's pretty ubiquitous now, and it saves some time for this kind of stuff. So it kind of makes sense, and it's there so that people can, write stuff or change stuff as necessary. Open source as well. That's the other thing. If something's going to have some longevity, it's going to need to be open sourced, and that's complete open source. The electrical design, the software design, and the cases. Run off a 12-volt DC power supply, and that would be for lithium batteries and lead-acid batteries as well. So there's quite a wide range on this. It will run from about 8 volts up to 18 volts. So no need to worry there if your battery's running low, or it's an older battery, or you're running lithium, you're running at about 13 to 15 volts. Switchable camera sensors. So we can actually literally just camera sensor out, plug it, and plug a new one in. So designed for occultations or astrophotography, and mono or color as well. So we can actually use a mono, literally a mono sensor or a sensor. We can use both. Excuse me. Okay. Has two. Plate solving. Plate solving takes around 5 seconds. And I've been plate solving both on Red Cat 771 and the 9 1/4 inch HD I've got polar alignment. So at the moment I've got polar alignment for negative scope, but I will be adding others, like 2 and 3 star. At the moment the polar alignment is take a photo, so roughly get it pointing in the right direction. Take a photo, rotate 90 degrees, take another. It tells you what the area is, and you move in an altitude and azimuth by that amount, and you take another photo. It tells you how much you have to move again until you iterate until you're down to minimum error. Now for occultation, it's arguable whether you need that, but it's there. Certainly for astrophotography, you're going to want it. The other is designed for the task, so that simplifies things a bit. And future plans are to get automation and planning in there, so that you can take multiple, you can run multiple or unattended events and things like that. The ability to download occultation, so there's always possibility of error in transferring RA deck coordinates between systems and times and things like that. So the ability to download occultations directly OW cloud. General idea is to reduce user error where possible. That's user error in recording and user error in setting up. Also having an audit trail, so having an audit trail or timing and the event, having an audit trail for getting position the person that was at well, and the outage, of course. And the other thing is raw data. So we want compression, we want raw data, obviously, because it's scientifically more useful to us. From triggering, which will just saturation detection would be nice, so we can tell if a star we're interested in or any of the tracking stars are saturated. That'd be useful to know. And at the moment, I'm using a custom file format called RAVF, which I've written a spec for. But plans are to change it to AVVD to add that spec update for that when the design's finalized. Okay, so this is what it looks like. So on the left, we got the back of the device, middle picture top. That's essentially just to remove the lens cap, plug it into a 1 1/4 inch adapter on a scope. If you want others, like I have mine, I also hook mine up to via 48mm as well. Do the output for the camera is a CS mount, so you just need to convert it to go CS mount to whatever you prefer. On the right, you can see I've got it hooked up to my Red Cat 71. That's inside the sensor. For the first bottom left is inside the sensor. There's the LED in there. That was just the first version. I actually got the LED mounted different, but I was mounting it in directly into the 1/4 inch adapter initially. And the other two, which as you can see, it hooked up to. So what's important to note is a self-contained unit. You've got a connected power, and you have a connection to mount. And if once focusing is running, then you'll probably have a connection to your focuser. Well, but that's it. There's no connections that are needed. So another close up of the picture. This is actually a video showing you as a right around the thing. At the moment, I've got it hooked up to an external GPS, which is why there's GPS cable coming out. The reason for that is I get a pretty lousy signal in some off, so I just have an external receiver just so I can test the GPS adequately. But there is actually a GPS antenna built in the device as well, so that won't be needed in practice. So there's a general overview of the design. So the whole unit is called ASTRID, and ASTRID could be used for astrophotography or occultations. If you want to use it for occultations, use OTE stamper to time the occultations. So the standard board is optimal for astrophotography, but it's not optimal for occultations, because if we're doing occultations, which is we need to have it timing. And then the camera, see, you can choose which sensor you want to use. This is the software. So essentially, software plates are in polar alignment. Go to we'll have catalog stored on as well. Mount controls via IndieLib, which some of you are probably familiar with. IndieLib is basically a system to make hardware platform agnostic. However, you think, well, why didn't you use it for the camera? The reality is that drivers aren't good enough to handle the work that we're doing with the precision that we need with IndieLib. So that wasn't an option for the camera, but it was an option for things that would be a heavy, like for instance, mount control. It's nice if it's a bit more standardized. Same with focus, so that people can have a variety of mounts to choose from, or focus to choose from. It also has mount sync as well, so you sync your current position to mount. And then for astrophotography, so the astrophotography support at the moment basically it's got dithering, do multiple subs. I'll be putting his camera on there, and it's already got auto stretch on there. So for OTE, you're going to want stars of interest, details on the timing accuracy, obviously no compression, planning support, and account onto the event as well. Okay, so first thing you need a camera sensor. So I went through a number of camera sensors, as you can see here, to see which one were candidate, and also comparing them out there currently for ASTRO cameras. So for example, there's quite a few ZWO cameras in here. It's not that we would just ZWO camera, but the sensor that's in there is of interest to see if it's up to snuff to actually use for this kind of stuff. So things like QE on the read noise, who manufactures the camera, who manufactures the sensor, what the price is, things like this. First one that I evaluated with was Raspberry Pi came out with a shutter camera, which was the IMX296. So some of the first testing was with that, which is a color sensor, but we've also managed to source a monochrome sensor, which we're going to be using instead now for that same sensor. Also, shutter is kind of for occultations. There's also another one called the Raspberry Pi Q, which is based on the IMX477. That one is kind of interesting for astrophotography. It can do really long exposure, and it's color. And there's also some other candidates as well. And also we got the the QFY GPS 174 uses the IMX 174, and that's the same as the ASI 174. That's down here on line 28. So you can see they use various technology for all these sensors as well. You've got Prejudice. So Prejudice tends to be global shutter. You've got X more RS. You've got the Starvis. Probably all these names you've heard of. So this camera settled on for occultations with this one. This is a Prejudice Gen 2 sensor. It's frontal illuminate. Ignore that about that because of the color one, but essentially it's the mono version we're using now. It's the same specs apart from just mono. Pixel size 3.5 micrometers, which is similar to what you get in a regular ASTRO cam these days. Sensor resolution is 1456 by 1088, and it's got 1x binning. Read noise is quite nice, 2.2. Dark currents 3.2, and full well capacity is 10.6, and the peak QE on that is a C68%. Maximum exposure time is 15 seconds, which isn't a problem because we're normally exposing for a lot less than that. Okay, no IR cut filtering either. Okay, so essentially it came down to two. It came down to the mono. It came down to one this version, mainly because the IMX296 had the grain trigger out. and a global shutter. If we compare that to the QHY GPS, which is another camera you folks use, see here that the IMX 174 is Prejudice Gen 1, and the IMX 296 is Gen 2. The QE is slightly better, or looks slightly better. I'll get into that in a minute on the QHY Y14 at 77%, and on the 296 it's 68%. And the pixel size is on the QHY is also 5.86 versus 0.45 micrometers. So let's look at the so quantum efficiency. So quantum efficiency is the amount of photons you get versus the amount of electrons it's creating as far as a signal is concerned in the electronics of the camera. So it would be ideal if we could get 100 quantum efficiency, and theoretically it's probably possible to get better than 100% if you're using lensing and things like that. At the moment, the maximum you ever see is around 90% typically in the typical ASTRID Rasberry Pi. But there's a bit of catch. So when they quote quantum efficiency, they always quote peak quantum efficiency. So look at the red line in two graphs, the QHY GPS on the left and the IMX 296 on the right. And you immediately see that the peak quantum efficiency on the IMX 174 is higher than the IMX 296. However, if you look at the rest of the curve, the second generation Prejudice 2, so Prejudice Gen 2 on the IMX 96 actually does better than it does on the 174. I.e., if you're going for peak quantum efficiency as being the marker for a sense, not quite the whole story, because we're not just interested, in this case around 500 nanometers wavelength. Not just interested in blues and purples. We're kind of interested in light across the spectrum. So, really, a perfect situation would be flat. But in this case, the Gen is actually slightly better than the Gen 1 because it's better at more wider lengths than is on the Gen 1. And then we all hit Starvis, and how we should how it's for astronomers because it's got the word star, and that's the issue is when they came out with the Starvis sensor, is they reduced the size of the pixels mainly for doing security cameras, and when they did that, the bearing that was in front of so if you imagine a photodiode behind that receives the photons, and the light has to get to the photodiode, and most sensors put the electronic to pull off the data from that photodiode on top of the cell between that and the light source, right? So that attenuates the light source slightly. Whereas with Starvis, the sensor was so small, the pixels were so small that the attenuation was quite high. So what they ended up having to do was backlight it and put the electronics on the backside of the photodiode, not front, so it didn't attenuate it. And because of that, got some different efficiencies, right? But they are for smaller pixels. So if you look here and look at the quantum efficiency of the Starvis on the right, and the QE is around 86%. I've seen this about 91% on some of the sensors. They just vary slightly. We'll see that the MX 296 is down 68%, right? But does it matter? Well, most of the response is actually fairly similar on the right hand side. For instance, if you take 700 nanometers on the I296 is about 47%, and on the Starvis is actually about 43%. So it's actually less, and kind of follows on for the rest of the curve. as well. So that's kind of interesting too. Like everybody thinks that a lot of people think that Starvis is better, and certainly I did when I started looking into it, because it's got the word star in it, and you see the high quantum efficiency. But in reality, it doesn't really that much apart from a certain frequency of light in the blue and violet range. Okay, so current state of the project. So I have it talking to an AM5 mount from ZWO, because that's what I have. They're quite nice mounts as well. They weigh gears, and I've also got it working on an ASTR SC, because I have access to one of those as well. I'll be getting it working on a I remember the name up now. Well, anyway, one of the other like the EQM35, I'll be getting it working on, and all the mounts from that company when I remember it. Okay, plate solving is working. And it's working well. Polar alignment's working well. Go to choose working perfectly. Like I can like plate solve, literally plate solve, go to plate solve again, and the stars, and then go to and the stars dead center. Geo flips working. I've already done one occultation with it as well. I've done some astrophotography with it. The firm for the OTE stamper, so the GPS, the LED, and the frame trigger, that's basically now just got to interface that with the main hardware. Testing so far, one occultation, done a bit of astrophotography with it as well. Global, I tested global shutter and rolling shutter. I tested all the polar alignment plates, etc. There's a minimal use phase currently, so I need to be able to start testing it. So it's workable. It's not pretty yet, but it will be pretty. I built six boards as well. So this is how the polar alignment works. So I'll just give you an example here. So choose polar line, take a quick step to do the first step of the polar line. So let's take a picture first of all. The one's about a 5-second picture, I think, from memory. So it gets the picture. I can see the stars there. This is with the original color sensor. So as I said, we're using 1.0 now. It plate solves it, so it's doing the plate solve now. It's now plate solved. You can see the ray and deck down the bottom. It's now rotating the scope by 90 degrees. And it's going to take another 2 when it's done that. Scope's now as soon as it started tracking, now taking the photo. It's now got that photo, and now we're going to solve. There you go, solve. It solves done. Seconds. There you go. And now you can see down the bottom, it's got the azimuth 0.57 arc minutes east, and I need to move 2.57 arc minutes down. So it actually tells you how to move the mount. You adjust the mount, then it takes the next photo, and you repeat until you've got your error down to a minimum you're satisfied with. For astro imaging, you probably want to be down under 2 minutes typically. Okay, so this focusing, just to show you, it's just a video focusing. This isn't automatic yet, but it will be. I'm using a batten off masks. Okay, so go to. This is an example of go to. So I want to go to Vega. So I punch Vega, tell it to go in. You can see the scope slewing here. Okay, I'm going to take a photo to see if I'm a target. There you go. Now we do the plate solve. This is typical for the sky anywhere. So yeah, plate solved, obviously it's not centered because it's the first try, right? So I take another pic, and I place that. and then I go to that. And we'll see how it does. So I sync mount so that we know where we are. And we go Vega again. Take a picture. And Vega's dead center. So that's typically, so a rough polar line, but that doesn't really matter too much. You can do it in the general direction. You literally say, go to Vega, take a photo, plate solve, set them out, to Vega again, take a photo, and you dead center. And that's typical with good. You know, things like that, like for the ASIA or some of the others that are out there. Okay. So first rotation. So that's information rotation. I'm going to speed this up a bit. It was about I think it's predicted to be 4.2 seconds long. 4.3 seconds, although we measured it as 3.3. And hit light curve from it. This is the first test we did. It was a tough one too, because it was nautical twilight, halfway through nautical twilight, 11th magnitude star. Well, 10.7 magnitude star. It's a tough one to acquire anyway. It was also close to the moon. It was actually, I'd actually see daylight and ground, because we don't get full astronomical darkness up here for certain times of the year as well. That was the light curve from it. Signal to noise ratio on this was 4, which Steve told me quite good. And then so just going to switch over to let me get the right one. Okay, so this is the actual file that I recorded. Let me just find my mouse. Just bear with me here. There it is. Okay. So I've altered or patched Pi movie to be able to read the file I defined. So I'm just going to load the movie from that night. So movie.raf. So movie is now loaded, and on the right we've got the stars. So first of all, this is Pi movie, so we don't see the stars. Just going to move this down a bit so we can see it a bit better. So there you go, let's say that one. So our star of interest one here. So I'm just going to zoom in on this one so we can see it. Hoping you guys can see this, okay? And I'm just going to play this. If you watch these, so that was a flash. I just put an extra flasher on just to make sure, in case there were any timing issues, I want to make sure that you had the data. There you go. You go, see the star. Star disappeared there. So I'm just going to move back again. There you go. So do that. One frame at a time. Stars there. Stars gone. And a 3.3 event. You can see all the timestamps on the left side down here. Yeah. Okay, back to the presentation. No, the other one. There you go. So how does it do on imaging? So imaging, it's like anything, you just take a photo. Just specify the number of seconds and take the photo. So you can do multi-shots as well if you want to get stuff for stacking. It's basic at the moment. It does just dithering, so you don't have to worry about things like walking noise. And these are the images that came out of it. So when you consider this sensor costs $47 US. This is the color. This one's the 8 camera, the IMX 4 and 7. So this one's one I recommend for astrophotography. This is on a Red Cat 71. So you've got the supernova there, the recent super we had as well. This is the global shutter camera. So it's the idea that even though the global shutter camera only does 15 minutes, it's all passable for photography. We did some forest fire, so the images quality isn't the best, but but it gives you an idea where it's come off. Okay, so let's get connect to device. So this is how you connect to the device. I've actually got a device in my office down here. So I'll just connect to it. I just need to get my mouse back in. Some reason it disappears on when I switch screen sharing. I have to do that to get it. Okay. I'm hoping I got the right one. Okay, so I'm just connecting it over VNC. So this could be VNC running on your laptop. It could be VNC running on your iPad or iPhone or Android. So I'm just going to, so this is the face. So you've already seen this. I'm going to switch it over to video. So it's on video now. So it's too obviously because the exposure is too high. Drop that down. So this one can actually do frame rates down. Sorry, I just typed the wrong thing there. Let's start it again. So still developing in progress, and all these demos you always get something goes wrong. So it starts up. So there's no Mac connected at the moment, so I just have to wait for that to error out because I don't have a mount connected to it. There it goes. Okay, again. So switch over to video, and then I'm going up the frame rate. So this sensor will do 60 frames per second, and there are options to get other sensor at a later date which will do higher frame rates as well. I'm going to up it to 240. What that does is that's down the exposure time as well, so it's equivalent to 240, but it's running it at 60 frames per second. So I'll switch that over. You can see it's switched over there. See that's running away there. Timing information on the top. Now the screen doesn't get priority. The data stream is priority. So the raw video always you want to get accurate and fast rate and good quality. So that always gets priority over screen. There's things like all those stretch zebras you'll be able to put on, things like that. That's kind of how that works. So I was going to quit that, switch back to the presentation. Right. Do it this way. Okay. There you go. Back. So the OTC stamper had a GPS on board with the PPS signal on it. Just highly accurate. It's got an LED next to the sensor, which is optional. Frame trigger. So the response time on the frame trigger is about 4.3 nanoseconds. So we're not really too concerned about how long it takes for it to register that the frames come through. Timestamp accuracy I'm seeing at the moment is about 1.25 microseconds. Again, probably 3 or magnitude better than we actually need. The 12 volt supply giving. So you plug 12 volt in, it's center positive, so fairly standard. There's also reverse polarity protection in there as well in case you hook up the battery the wrong way. There's a fan on board, which can be switched off if you're concerned about vibration at all on higher focus. The firmware on the board can be updated directly via the Raspberry Pi. I don't need to be hooking up programming cables or anything like that. It's just a command you run and it updates the firmware. And, these are what the boards look like. So I had at the moment I'm hand assembling these myself. And I ordered the blank PC from OSH Pi, which is why it's purple. And you can see the GPS receiver on there. GPS receiver is basically the same as a U-Blox Neo 6M, but it's a version. It's got the same chip essentially. Sort of boards like. So this is a new version of the LED. So for time indication, I put a LED on there, so you can see it's right at the base of the adapter, and it emanates straight onto the sensor. You can also see the copper board on there. That will be purple at the moment. It's just the board that I'm using. That's just a board to extract the vertical sync signal off the board, and that essentially it just gets on top of the existing camera. and you can see a 3D render. That's the middle one is the original board CNC'd to build up the original prototype to test it. And right is the results of the jitter testing on the GPS clock. You can see it's pretty good. So that's based on the signal from the GPS and the crystal using a low drift higher accuracy crystal from the little microcontroller that's in the timing board. And as you can see, most of those are, with a quarter of a microsecond. So when I say it's 1.25 microseconds, it actually is 1.25 microseconds, and that's kind of like a the outline of it, not standard deviation or anything like that. The case is printed at the moment. I noticed the case is kind of squarish. It's just that's what I decided to do the first time. It doesn't have to be that way. There's a case for instance, for hyperstars, to have it to have the electrons vertically orientated and in a round case, so they don't produce any aberrations. And I know that quite a lot of people are using celestial with hyperstars, and it's at 2 and F3. So the case options as well, doesn't matter what electronics is mounted in. At the moment, I'm just 3D printing it on a resin printer. Okay, I think I just did the live now. So okay, so current status are 6 boards to be built. 4 are allocated, 1 to Steve Preston and 1 to Bill Young, who lives near me. So it's just convenient for me to be able to test another setup as well. And we go out and do everything together. And also I've got 2 that I'm using for testing at the moment. Occultations are working, general photography is working, future work, obviously its development is in progress on it. It's at a minimal level to do the task at hand at the moment, but planning obviously user interface improvements and support more mounts. And obviously if someone has a mount that they want it to work with, supported by NVIDIA, then I would work with them to help that become a reality. I'd just like to say huge thanks to Steve Preston. He's very instrumental. He contacted me shortly after I started this project and give me lots of ideas, improvements. I'm cognizant of the fact that I've done a couple of occultations now, and I don't have all that experience. I might know a bit about electronics and the software and stuff, but the actual doing the occultation is something that I'm kind of itchy on. It's been great to have that help, and also shout out to Bob as well for helping, Haristo as well. It's been very helpful. So if you need to read, best place is Twitter or Facebook. If you just put in at Chasing Spin, and you can find that way. Does anybody have any questions?
Yes, I'm curious how you're verifying the timing on that. Is there any external timing verification tests that you've done?
Yes. Not yet. I mean, when Steve gets the opportunity to do that, I'm not concerned, and I'll tell you why. The 1 PPS signal that's coming off the GPS is extremely accurate, about 1.25 nanosecond, and the timing that's coming off the board. So what it comes down to is timing it on the Raspberry Pi. I'm timing it on the Stamper board itself with a dedicated microcontroller, and I can tune. Essentially, I know what the offset is, a crystal on the microcontroller. So the jitter ends up just being the time to recognize the framing pulse signal, which is about 1.25 microseconds, because that's about the speed of the clock. So because it's running at 8 megahertz. So as far as verification is concerned, a lot of it is more once you've ruled the possibility of software being an issue, and you've got accurate timing there, then all you have with is how accurate is the hardware. Of course, the hardware is extremely accurate because it's doing the actual job. So the vertical sync signal that's coming out of the frame timing pulse will be spot on, right? I do have the LED on there as well, just so that I can check that the frame timing pulse is in time with when the shot starts. Because there is one horizontal sync pulse it has to have, or it actually throws out the vertical sync pulse. So I do actually have a check, and I've got the LEDs there just for testing during development, to making sure that the time 100% accurate. Does that answer your question?
Yeah, I think it does. Yeah, nice. Thanks.
Any other questions?
Well, Mark, thank you very much for a very enlightening presentation. And hopefully this will be a very useful adjunct to our occultation observations in the future. I'd like to go on now to our